Hello everyone. In last lecture we have studied about equivalent conductance, molar conductance and their relations and the effect of dilution on the value of equivalent conductivity. We have also seen that in case of strong electrolytes, the values of equivalent conductances are now increasing in nature. And again keep on dilution, we have to reach the maximum value of this equivalent conductance up to a certain extent, and after dilution this value is much steady in case of strong electrons, and that value is called as, that is equivalent conductance at infinite dilution. Okay, that is equivalent conductance at infinite dilution. Also it can be denoted as lambda v of a decimation as a standard. That is, this is also known as a standard or infinity. In some books we have given the infinity, in some books we are given standard. Whatever you want to use the word, you have to use. But in case of weak electrolytes, what happens? In case of weak electrolytes, the values of this equivalent conductances are not coming to a maximum value. They becomes increasing as like this in the graph of equivalent conductances versus concentration. Therefore, we do not get the correct value of equivalent conductances at infinite dilution. For that purpose, we have the new method, that is measurement of conductance by using Wheatstone's bridge method. Okay. Now today we are going to discuss this method in detail. Before studying this method, we have to study in which way we have to study the measurement of conductance. For the measurement of conductance, we have to measure first the resistance of a test solution in which we are given to study. Okay. Now we know that resistance R is equal to, we know that this resistance is the definition of a conductance. In which way? That is, conductance is defined as the reciprocal of a resistance. Already we have known to this quantity, and by using this quantity we have to use the principle behind this Wheatstone's bridge method. Now what is the principle behind this Wheatstone's bridge method? See here, principle: known resistance is opposed or compensated by unknown resistance until they are equal. Until they are equal. That is, whatever may be known resistance, we have to carry out from the resistance box by using Wheatstone's bridge method. When this resistance is in equivalence portion of this unknown resistance, we get the null deflection. That is, we get a minimum sound through the brass tips containing the reading on the scale by using this Wheatstone's bridge method. Now what is the diagrammatic representation behind this? See here, diagrammatic representation. For that diagrammatic representation, we have to use the resistance box. Okay, first of all I will give you the concepts and then we will draw the diagram. RB means resistance box. Suppose Rx is the unknown resistance. Of a test solution. Okay. Now J is the sliding contact. AB is a wooden plate, wooden meter scale, which is located on the brass strip. In order to, we have to move this sliding contact through this AB wire. After connections are made completely, we have to slide on this meter scale through the use of sliding contacts. We get the buzzer with the help of headphones. So we get the sound. That is, the understanding of our connection is ready. Now what is the diagrammatic representation? See here. This is the diagrammatic representation of measurement of conductance by using Wheatstone's bridge method. First of all, we will see about its construction. It consists of a wooden plate in which brass strip is located, in which a meter scale is placed. In this meter scale there are some readings. Okay. Now this is the one end of the brass meter strip and this is the second end of the brass meter strip. From first and second end it is attached to a oscillator for its electrical contact. Now some resistance box is kept through these connections and some resistance is taken out from the box, and that resistance is known as known resistance. We have to measure by using Wheatstone's bridge method, that is the resistance of the unknown solution, and by taking its reciprocal we get the conductance according to our definition. For that purpose we have taken the test solution in a container in which two electrodes are kept apart from each other, in which the electrodes are dipped in the test solution. Before dipping the electrodes, these electrodes are first washed with conductivity water, okay, and then they are rinsed with the test solution. Then they are dipped into the proper place through which electrical contact is done through this Wheatstone's bridge method. Once the circuit is completely made, we have to check it by joining the oscillator on the induction coil through the A and B end. Okay. Once we get the higher sound through the galvanometer or headphones, okay, we get to satisfy the completion of a circuit. Now working. Before working, we have to attach in this rectangle through a jockey through a sliding contact on the brass metal plate in order to get the buzzing sound or the longer sound, and the galvanometer shows the null deflection. Okay. Now what is the working? Okay. Once you take this jockey and after the completion of the circuit by use of a oscillator or induction coil, we will place this jockey through this wooden plate or brass plate through as like this. When it shows a null deflection, at that time we get the minimum sound through the headphones, and that point, suppose this is at this point, that point is called as null point, okay, or null deflection reading. At that point we have to measure, suppose this point is called as a C, we have to measure the distance AC, length AC and the length BC. By taking the ratio of length BC to length AC with respect of in saturation with correspondence to the unknown resistance, whatever may be the unknown resistor we get at that time, through this point we have to note down. Okay. Suppose at this time we get the null deflection or the minimum sound, and the resistance to be is equal to X ohm, okay, of this test solution. Now what is the calculation? By taking the ratio of unknown resistance to the known resistance. Already we know the known resistance. By taking the ratio of unknown resistance to known resistance with respect of corresponds to length AJ to length of BJ, we get the resistance of unknown solution. Okay. What is the calculation? See here. Calculation. Unknown resistance of test solution divided by known resistance equal to resistance of wire BC divided by resistance of wire AC. Okay. What is the unknown resistance? That is Rx. What is the known resistance? We have to write here Rb is equal to resistance of wire, that is equal to length BC divided by length AC. We have to calculate this factor. Therefore, cross multiplication taken, that is Rx is equal to what happens? that is RB into length BC, okay, divided by length AC. Already we know these two quantities from our Wheatstone's bridge experiment. RB already we have known by taking the ratio of this, whatever may be the quantity, that is the unknown resistance of the test solution. Our aim is that is to calculate conductance. How will you calculate the conductance? Already by definition, C is equal to 1 upon R. Already we have shown in our first lecture, that is C is equal to 1 upon R. This quantity we get from this experimental conditions. Put up this and take its reciprocal, you get the conductance of the unknown solution. Okay. Now in this way, by using Wheatstone's bridge method, one can calculate the conductance of a given solution in case of a weak electrolyte. Okay. We will study the basic circuit for Wheatstone's bridge method. See here, diagrammatic representation. Okay, this is the basic circuit for Wheatstone's bridge method. Okay, in which these known resistance R1, R2 and R3 are the known resistance and Rx is the unknown resistance. This is the detector in which galvanometer shows the null deflection. After attaching these circuits, we get the resistance as, that is R1 upon R2 is equal to R3 upon Rx. Okay, therefore Rx is equal to R2 into R3 divided by R1. Schematically in physics also there is a use of this type of circuit, and thus the unknown resistance of a solution is calculated by, that is the ratio of R2 and R3, that is the known resistance, divided by its Rx divided by R1, we get the unknown resistance. Okay. Now there are some problems by using the direct AC circuit. Okay. Due to direct AC circuit, alternating current or DC circuit, there are some problems. What is the problems? We have to take the test solution. Okay. When we are taking in test solution, in which electrons are dipping to this test solution by using this type of alternating DC direct contact, at that time electrolysis of the solutions containing ions takes place. Therefore, we do not get the correct resistance. For that purpose, we do not take this type of circuit. Okay, thank you. Now we will discuss the another law, that is of Kohlrausch's law. Before seeing this law, we have also seen that is electrical conductivity or equivalent conductivity at any dilution which reaches to a maximum value, and that electrical conductivity or equivalent conductivity is also called as equivalent conductivity at infinite dilution. Okay. Now by taking the example of some electrolytes we get the different conclusions. What is the different conclusions? According to Kohlrausch, when we take the KBr as an electrolyte, we get the electrolytic conductivity or equivalent conductivity that is equal to 0.05192. When we take KCl, potassium chloride, we get the electrical conductivity as 0.014980. That is when we differentiate between the anions by placing cations of same quality, we get the constant difference between the electrolytes is 0.000206 in any of the electrolytes. Also, when we kept here cations as a constant value, constant criteria, when we place anions are the same and the electrolytes are different, what happens? By taking KCl and NaCl as a strong electrolyte, we get the equivalent conductivity as 0.01496 and 0.012 or 645 conductivities values, and this difference is lies to be 0.02341, and this difference kept as a same when we take the different kinds of cations but same kinds of anions, which suggests that each ions makes its own contribution to the solution remain. That is, whatever may be there is change of cations, there is change of anions, the difference between the strong electrolytes is the same, and the difference between when the anions are same and the cations are different, the difference between the same. These two values are becoming constant position. Thereby, the scientist Kohlrausch suggested a law, and that law is known as Kohlrausch's law at infinite dilution. Okay, at infinite dilution means we have to study in last lecture, that is lambda v at infinity or lambda v at standard. You can use any of the notations. Okay, now what is the statement? See here. Statement. The equivalent or molar conductivity at infinite dilution is the sum of ionic conductivity of their respective cations and anions. Anions at infinity. What is the statement? Again, I will repeat this. That is equivalent or molar conductivity. That is lambda v at infinite dilution. We have to write here designation as a infinity, or lambda v of standard is the sum of ionic conductivity. That is, there is formation of a ions due to the dissociation in a solvent. That is lambda infinity plus lambda infinity of respect to which criteria? That is cations for plus and anions for minus. Mathematically, it can be designated as lambda v infinity or lambda v standard is equal to the sum of ionic conductivities of their respective cations and anions. Okay. Now, again I will write this as, that is equivalent conductivity, what is? That is lambda v at infinity, that is equal to infinity, or lambda v of standard, okay, is equal to ionic conductivity. Ionic conductivity of which electrolyte? That electrolyte we have taken its a equivalent or molar conductivity. That is lambda standard plus lambda standard of its cation and its anion. At which position? At infinity. Okay, therefore we can write it as a infinity or standard. Now this is the mathematical form of Kohlrausch's law. This is a very simple law. In the problems we are given 3 electrolytes, and from the 3 electrolytes we can calculate the value of a equivalent or molar conductivity at infinite dilution. See, we take some problem for our simplicity of understanding. See here, I will take one problem. Calculate equivalent conductivity. Calculate equivalent conductivity at infinite dilution of acetic acid okay, at 298 Kelvin. We are given that molar conductivities of infinite dilution of same temperature, molar conductivities of infinite dilution of electrolytes such as lambda 0 of HCl, lambda infinity of CH3 COONA, okay, and lambda infinity of equivalent conductivity of a NaCl. The values are, here what are the values? That is 0.04261, okay, here 0.0091, okay, and third value is about, that is 0.01265 Simon centimeter inverse. Okay, we have to find out the calculate equivalent or molar conductivity of a acetic acid. First of all, we have to write the chemical equation in a dissociation form. Okay, see here, solution. According to Kohlrausch's law, we have to write the reaction for these electrolytes. We have to calculate which of, that is lambda infinity, that is molar or equivalent conductivity of a CH3COH, okay, that is equal to, what is the lambda 0 of CH3CO minus plus lambda 0 of which, that is H plus, okay. Now first of all we have to write the reaction, that is CH3COH can be dissociated into CH3COO minus plus H plus. Okay, again HCl dissociates as a aqueous solution. Here we have to write the aqueous solution. What is, that is H plus plus Cl minus. Okay, and for CH3CONA, that is CH3COONA gives rise to CH3COO minus plus Na plus. Okay, write is as number 3, here number 2, okay, and here as a number 1. Now observe these 3 chemical reactions in a aqueous form. We want, what is the, that is the CH3COH, okay, that is we want this reaction, okay, this is the 4th reaction, okay. What is the reaction? Suppose this is very simple to this, okay. Now what is the reaction? That is, we have to write here again as, that is NaCl as here Na plus and Cl minus. We want which cations here? That is CH3CO minus and H plus. In between these reactions, which HCl, CH3CONA and this NaCl, whatever these cations are present and whatever these cations are absent, we have to subtract it. Okay, from HCl we get HCl, that is we have to add this second reaction plus CH3COO. Okay, that is we have to add 2 and 3 reactions, and from 2 and 3 reaction we have to subtract the 5th reaction. But we know what is, we know that is equivalent or molar conductivity of infinite dilution. Therefore we have to take the sum of these 2. Which of 2? That is the lambda infinity of HCl plus lambda infinity of CH3CONA minus lambda infinity of NaCl. Okay, now here I can write here as that is lambda infinity of CH3COH is equal to lambda infinity of CH3CONA plus lambda infinity of HCl, okay, minus lambda infinity of NaCl. Got it? Therefore, we can take the values as 0.0091 plus 0.04261 minus 0.01265. Take the sum and then subtract these values. Here, what is the answer? 0.0091 plus 0.04261. Okay, I am taking the total as 0.04261 plus 0.0091. Okay, 175 From that we have to subtract it as 0.01265 as that is 60943 0.03906. What is the final answer? That is lambda. Here I can write here as that is lambda infinity of this which electrolyte CH3COH is equal to 0.03906 Simon centimeter raised to inverse. This is the final answer. Okay. Before getting this final answer, what we have to take? We have to write the dissociation reaction in form of chemical reaction. Then we have to subtract these values of the standard or infinity values of equivalent molar conductances of particular electrolytes, and then whatever may be the remaining, that is unused part, that is we have to subtract it. In this way, we have used this Kohlrausch's law. Thank you.